guys for coming. Thank you. Thank you guys for coming. It means that you want to learn some new things and see what's going on with Gradle. I'm very happy about that. I'm Stefan Faber. I'm the tech lead in development tools at LinkedIn. Why I want to talk about composite builds is because my team and myself, we are super excited that we are able to roll out composite builds at LinkedIn. And here's why. So back in 2010, 2011, LinkedIn just started experimenting with Gradle. We didn't know that Gradle would be a big thing in the future. We were just trying this out on a handful of projects. Another thing was that we had most of our services implemented in one single giant code repository, like a monorepo. Over the years, Gradle was taking over at LinkedIn. So we started onboarding different technology stacks, not only the standard flagship stack for Gradle that used to always be JVM, now it's also Android. But now at LinkedIn, we also use Gradle to drive C++, to drive mobile, and not only Android, and also other platforms like JavaScript. What happened also is that we decided to go to multi-repo architecture. So remember our services, they used to be in one giant massive code repo. We decided around 2011 that that's not a good idea. We want to invest into multi-repo architecture where software components are developed in separate repositories by separate teams. We also invested in a lot of tools to make it possible to make it successful, right? And this is where composite builds kicks in. This is how it all connects. When you go multi-repo and you break down your software into components and teams work separately, you have this problem that sometimes your change spans multiple software repositories, multiple repos. So what do you do? What we have at LinkedIn is sometimes people miss this mono-repo style where you had all the code, you could refactor as you wanted, you could browse and navigate the code easily. Well, so long you waited enough for it to load to your IDE, you waited long enough until it checks out, and you had other scalability issues. There were still some advantages of monorepo. We at LinkedIn, we continue our effort into closing those gaps and adding features to our multi-repo architecture so that it's really productive. And this is where composite builds kick in. I'll show you a demo in a second. Before I show the demo, I want to tell you that it's not only Gradle composite builds that we at LinkedIn leverage to make multi-repo architecture productive. We also write our own Gradle, our own IntelliJ plugin, for LinkedIn-specific features and tools for IntelliJ. This also helps us out a lot, and we actually have some team members, Baron from that team. If you're interested how LinkedIn leverages IntelliJ and intelligent plugins, socialize with us and you can find out more. So let's see the demo, how it works. So I have an IntelliJ open here. So one thing you can see is that I have a checkout multi-product option and open multi-product option. This is something that does not exist in stock IntelliJ. This is something we have developed as our plugin. Multi-product is at LinkedIn an abstraction over an software project. It could be a mobile app, it could be a native app, Python, Java. All at LinkedIn are multi-products. So the multi-product I will open is sample MP Java. And this is now the feature that I'm talking about. So I can actually check out multiple projects into the same IntelliJ, which gives me that opportunity to refactor and browse the code and use one single IntelliJ window to work on multiple projects. Sample multi-product git. I'm using hello world examples just to make sure it's working. So I'll do the checkout. I had checked out those projects before, so it should be faster. Oops, I see some errors. Ah, no! Oh, God. Yes, pre-recorded demos. That's what you should do. Hang on. Let me go here. Yeah. Okay, cool. I'm going to hit OK. Thank you for informing me. I'm going to hit cancel. Let's do it again. Sample MP Java and cross multi-product development. Sample multi-product git. Let me just quickly go to sample. don't worry, like everything under control. It's not IntelliJ's fault or even Gradle's, it's how we work. So you might have noticed that when I did that checkout, I had this warning that this feature is still like incubating. This is something we are still working on. So Gradle Composite Builds is already available with Gradle. However, there are a couple of things we still want to get implemented to get it really make it really good. We want to make it faster. We want to make it working better with different kinds of connections and dependencies between projects. Like if you have a Gradle project, Gradle plugin dependency to a different project. So while it's doing, we find it. Oh, cool. So I have 2 projects checked out now. They look as separate modules in IntelliJ. They're actually separate projects that they have separate code repositories. What I wanted to show you is that you have all the benefits of of working on the same code base in the same IDE. I have a method here, foo, that actually lives in a different project. So IntelliJ allows me to navigate there. I can rename that method. It's going to be renamed in the caller class, which is a different project. So I have all the benefits. And how it works, so it's Gradle Composite builds plus our IntelliJ plugin and plus like the features of IntelliJ, because IntelliJ offers you nice ways of linking projects together. And there you go. We have a very nice feature that bridges that gap from monorepo to multi-repo and offers LinkedIn engineers a way of working on separate projects in the same IntelliJ window. It's we still work on it. We will still make it better, but this is a starting point, and this is very important for us. It's also exciting for me and for my team because we were able to make a very nice partnership with Gradle Incorporated. This is where LinkedIn actually sponsors a feature that goes to Gradle open source, and everybody can leverage composite builds, and LinkedIn can offer that contribution to open source, or soon Microsoft. So I think that's it from like Hans. You want to take over?
Cool. Thanks. Okay, welcome. So you wonder about the slides. I'm just back from DevOps and Verb. You know, the DevOps conference will be in the Bay Area in spring, and I presented the latest about Gradle. So yeah, I did not adapt the slide templates, but hope you can deal with that. So what I want to talk about, I don't want to give the full presentation because other exciting stuff we want to watch, but I want to talk about initially what it means to scale builds, right? Because when people talk about scaling builds, right, they usually only think about build performance, right? Scaling builds means making builds faster, right? And obviously build performance is a very important part of scaling builds and build infrastructure, but there's much more, right? So for example, extendability is extremely important, right? If extendability is not good, you have a fast build, but it doesn't automate half of the stuff that needs to get automated, right? And then you need to create your own tooling for this. So it's a very, especially for complex enterprises with the custom requirements, it's a very important quality, right? Then the third one is deeply support developer workflows, right? So, and Stefan gave a good example with composite builds, right? Where we say, hey, in a multi-repo architecture, I want to have a good support for this workflow working with more than one repository at the same time, right? That is an aspect of scalability. And then number 4 is you can have fast and extendable build systems that are extremely painful for developers to work with, right? To configure, to change anything. And I've seen that multiple times. And you expose a lot of unnecessary complexity to the developer. So a good build system gives the build masters tool to tailor it in a way that it's easy to configure for developers, right? Then build infrastructure must be maintainable, right? And then there's monitoring and analytics on build infrastructure. So Luke and Etienne will talk about that aspect. And then there's the aspect of enforcing software health. And we'll talk about that also later. Okay, so so when we talk about build scalability, it has many dimensions, many interesting dimensions. So one thing I will not talk about in detail today is build output caching and the new Gradle distributed cache, which we are super excited about. I'll just give you a rough idea, right, what we're doing. So every Gradle task, who of you is using Gradle? right? So, and every Gradle task, right, has inputs, right? Then it has the actual implementation, the actions, the compile, the testing, and it has outputs, right? And for the Java task, it would be source compatibility would be an input, you know, configuration property, the sources would be an input, and the class path would be an input, right? And the output would be obviously, in this case, the compiled classes. Okay, so, and inputs and outputs are explicitly modeled in Gradle for a long time, right? You have annotations for that, right? You can annotate the setters, which are the inputs and which are the outputs of the task. And if a task does this, right, all the Gradle tasks that ship with Gradle do that, then whenever you run Gradle, we store the hash of all the inputs and all the outputs of the task. And the actual outputs itself is in the build directory, right? Right, and but we also hash this output and all the inputs, so that when you run the build again, we can run this build more efficiently. But important to understand, the build directory is part of this cache, right? So and then with this information, right, when you run a Gradle build the next time, right, we can now figure out same content. Has the input or the outputs changed compared to last time, right? And if they have not changed, the task is up to date. We don't run it, right? If they have changed, then we execute the task, right? And what is very important is to distinguish incremental build, which is this, from incremental task execution, or to distinguish between up-to-date checking and incremental tasks, right? So, for example, incremental Java compile, right? So this is a binary thing, right? This mechanism, something has changed, I execute the task. Now, in Gradle has an additional layer where now a task can decide, well, do I really need to rebuild everything, right? And we help tasks with that. We can tell tasks, hey, those files have changed. So if you know enough about your domain that you only need to rebuild a part of the output, then do it. Otherwise, clean everything and rebuild anew. But that is a different layer, right? This is a binary layer. Something has changed or not, right? And depending on that, we execute it. So, and every Gradle user knows the up-to-date feature, right? It's prominently shown on the command line, and but it's important to understand the detail, right? So the cache kicks in for a task when, right? When the content is the same the last time you run the build. So for example, when you switch between branches, right? Master branch, feature branch. You build the master branch, then you switch to check out the feature branch, you rebuild it, you build it, you switch back to the master branch. It's no up-to-date checking is happening, right? Compared to the previous time you run master, it will be compared to when you run the feature branch. We only store the content of the last execution, right? And at the end of the day, there's only one build directory. So how could it be different, right? There is one build output directory, and that is where basically all the content lives. So that is a limitation, right? The other thing is it has to be this build that is cached. So when you check out the same project from GitHub in two different directories, you run it in one directory, and then you run it in the other directory. When you run it in the other directory, you have to run it from, fresh. It's a fresh build. It does not reuse the output from the other directory, right? So obviously, obviously it has to be on this machine. Output between machines is not shared, right? And very important, without clean. When you run a clean build, you don't have any up-to-date checking, right? Some people may say, well, that is why I do a clean build, right? But we talk about this later, right? But it only works when you don't do a clean build. Okay, so and now I want to talk about the new Gradle task output cache, right? And it is not a replacement for the current up-to-date mechanism, which will continue to have its place. It is an additional caching layer, or potentially even multiple layers. Okay, so what is the purpose? Right, so we said this is this is basically, those are the constraints for the current up-to-date checking, right? And first of all, the new output cache will get rid of that constraint. We will store the complete history of build output of every build execution, right? And because it does not live in a build, it is not stored in the build directory. So that means you can switch back and forth between branches, and the build results of the previous builds, they're still all stored and reusable. So you will have a very, very effective switching between branches from a build perspective, right? The other thing is, it will work now in a scenario where you have the same project checked out in 2 directories, right? We will figure this out and we will reuse the output. Most importantly, it can be anywhere. You will be able to share build output between machines, right? And finally, even if you do a clean build, this is going to happen, right? So, that would be very good for CI builds. And we can do that because the content is not stored inside the build directory, right? The build history is kept somewhere else. So even if you remove the build directory, the build output of the previous builds is still accessible with the new cache. So what is required to get there from the Gradle side, and what do you need to do to make use of that, right? It's still in development. That is very important to understand. I will talk about that also later, where we are with that. So first of all, we needed to extend the input-output model to make this reliable and efficient, right? Both things are very important. So first of all, a task implementation has to opt in to be cached with the new output cache. There are 900 plugins in the Gradle plugin portal that have never thought about task output cache. If we would just say, oh, we just cache everything, there's a big reliability issue because they have not thought about what it means to be cached for eternity, right? So that is why you have to opt in. All the tasks that ship with Gradle will opt in. The Java tasks do already, right? But for your custom tasks, you need to explicitly tell Gradle, right? So reliability is king, right? And for example, if you have a custom task where you, let's say, a source code generating task, right? And you just say, oh, the task picks up whatever version of the source code generating tool is on my machine. Sometimes it's 1.0, sometimes it's 2.0. That is not output you want to share with other builds, where the version of the source code generator is not part of the key of the cache. Right? Person that run with 2.0 should not pick up the output from the 1.0 run. So they need to configure their task in a way that the key of the cache is reliably computed. In this case, has the version of the source code generating tool inside the cache key, and you do that with the annotation. So that is one part, right? You need to opt in. Then we have now annotations, right, where this is about efficiency. The is verbose setting should not be part of the cache key, right? Whether the command line outputs verbose or not is not relevant for the output. So even people that have it set to false or true, they should still be able to share the output when all the other settings are the same. And the most interesting problem of distributed cache, or one of the interesting problems, is what do we do about path? So at the moment for up-to-date checking, and that is the reason why it doesn't work when you have 2 different directories, we use the absolute path to calculate the hashes, right? So, but if we do that, right, you will have a very reliable distributed cache, but not a very efficient one, because you will not have many hits. So we have now added annotations where you can tell us the path sensitivity, right? So you can say it should be absolute, okay, then we do it. You can say it should be relative to the project root directory. You can say only the name of the file is important, let's say for class path, for jars, right? It depends on the domain of your task. You need to tell Gradle, but you can tell this Gradle now with the new annotations, right? So, okay, so basically our extended input-output model was a requirement for an efficient and reliable distributed cache. And then where should this new cache live, right? So there are 2 typical locations for this new cache, right? So one is on a shared server, right? And this is called a distributed cache. And the way it usually works is that the CI builds, they read from this cache and they write to it. right? And they usually always do clean builds, right? So they will heavily benefit from that. They often run different jobs with different user homes against the same project, the fast check, the long check. It's so heartbreaking how long we had to suffer that you use different jobs against the same project and everything was built again, right? So I know that you had some custom solutions for that because you couldn't stand it any longer, but it's this will now come basically out of the box, right? So and then the developer builds, what we recommend is that they only read from the distributed cache. That reduces the latency, and there's some reliability aspects in there, that you have controlled environments that write into the distributed cache, right? And our experience is not a lot of efficiency gains in the typical settings that we operate in with the larger teams, that you would get a lot of benefits from developers writing to the distributed cache. When I look, for example, at the LinkedIn CI infrastructure, it's so fast, it's so powerful. I mean, change is committed, boom, right? It would be in a distributed cache and it's built, right? So that is what we usually recommend, this kind of setup, but it's configurable. It's up to you. Whoever wants to write, you can give the permission to write. And then the other cache instance, and that is optionally, is on your machine, right? To reuse output, for example, when you switch between branches, right? That it is for that use case. Okay, so what are the elements of the new cache? So I talked about the extended I/O model. So part of that is most of that is already in 3.2. It will be finalized in 3.3. The Gradle Java tasks, they are already configured for the new cache. The native tasks, not yet. There's some other tasks that are not yet configured out of the box. Then a REST API and Java adapter to connect a cache backend, right? With the Gradle Distributed Cache API. Authentication API, we hope we have that both of that done by 3.3. Configuration DSL, so you can say, that you can configure it in a nice way and say who should write, who should read and write. And a cache backend reference implementation. It's also work in progress, something is already available. And then a built-in local task output cache, right? That you can at the moment take the reference implementation and install it locally and it will work fine. But we want to have, we want to soon ship a Gradle that comes with this new second layer of cache out of the box, right, for local builds. But at the same time, at the moment, we focus on making the distributed cache working because that is where you get the biggest bang for the buck. That's what we think, right, especially for larger teams. Yeah, so we're super excited about that feature. And just to share some numbers, so we have a performance test project that kind of simulates a larger Java enterprise build. It's public, right? So you can check it out, right? And we run that against the distributed cache. So no cache, the build took 300 seconds, so 5 minutes. And with the new task output cache installed locally, it was down to 5.8 seconds when everything was cached. And when the cache was on a different machine, it was 6.4 seconds. So very nice results. That's where you want to be, huh? Right? People coming to work in the morning and boom, right? No cup of coffee, sorry. Okay. So I just want to quickly talk a little bit about composite builds because Stefan already told the main story. So composite builds is about combining independent Gradle builds, right? And what does it mean, right? It means when you have two different repositories, two different Gradle builds, right? And they have a dependency between each other. This is the interesting use case. When they don't need each other, right, there's no point, right? They have a dependency between each other, and that is usually modeled when you have a multi-repo setup as a binary dependency, right? So, and what we do with the distributed, with the composite build is when you tell Gradle, hey, the composite is repo A and B, we check, does any of the binary dependencies refer to the other repo? And then we replace it with the source dependency. Then we tell Gradle, no, in this case, this is the composite. You have to rebuild the binary dependency from scratch, right, from the latest that is checked out on your machine. Right? That is how this works, right? And and I don't do the demo. Stefan did a demo. So, and there are many reasons for that, right? So it's quick local experimentation, right? How painful is it when you have two projects and what do you do nowadays when you need to do that, right? You work in A and you say, oh, I need a method in B. So you go to B, you change it, and then you go back. Where's the method? Oh, damn, I forgot to publish. So you go back to B, have to publish to my local repository, you have to set it up. You go back to A, you work again, right? And you say, oh, now I need this other method. Half of the time you forget to publish. It's so inconvenient and so painful at the moment to work with multiple repositories. It always takes you out of your flow, right? And what we do, right, with the composite builds, you stay in the flow. You tell Gradle, treat them as one build, right, and import them as one build into the IDE, which is now possible with Eclipse and IntelliJ. In the latest version of IntelliJ, they wrote a blog post about it a couple of weeks ago. So, and it's such a typical such a typical feature for developers. So we are a typical problem. So I think we're very excited about that. Cross-repository refactoring, that's what Stefan demoed. A special use case, imagine you had that, 2011, right? Migrating the big monolith to a multi-repo scenario, right? Many people are doing this at the moment, and this is a wonderful use case because it means a lot of refactoring usually to extract the piece from the monolith, and you can do this very effectively. Now, combine this with the distributed cache, right? It's gorgeous, right? Because the monolith build will be very, very fast for you, right? So wonderful use cases, right? And another cool use case is faster Gradle plugin prototyping. So who of you have ever developed a Gradle plugin, a standalone plugin, right? So you have your separate project, right? And now you want to test it in a test project. And it's exactly that scenario. Publish it, consume it, and this binary substitution also looks at the build script section. So when in the build script section you define, I depend on plugin, confu, blah, 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 and you now tell Gradle, those are the composites, we will replace it and rebuild the plugin always from scratch, and wonderful. Okay. Good. So final feature, last feature I want to talk about tonight, one of my favorite topics. It addresses many scalability dimensions at once. So it's about enforcing the API. So let's look at the following project. It's a multi-module that contains 3 modules, multi-module build that contains 3 modules. Core depends on util, depends on sumlib, and they have some external dependencies, right? So, and now when you compile core, right, what will Maven and Gradle put into your compile class path? Everything. Everything, right? Very generous, right? And the whole graph. So is that a good idea? No. Who thinks it makes sense to do it like this? What would be the alternative? Just utils and commons collection, right? Yeah, that's what I thought initially, and mostly it's the right thing, but not always. Anyhow, so but that is not the current behavior, right? And we talk about that in more detail. Why? But I think it's not a good idea. And just look at it from an API perspective. So basically, when core says it depends on utils, what it basically wants to say, at least during compile, I depend on the API of utils. And what the build system now says, well, the API of utils is all the code of utils, all the code of sumlib, all the code of commons lang, and all the code of commons IO. The surface of your API is gigantic, right? And should you bother about that? I think yes. So yeah, that is what is put in the compile class path. So I think this is evil, right? So a vast surface area of the API. So the graph is often multiple orders of magnitudes larger than necessary. It is not just a few libraries, right? When you look at the larger builds, so it's hard to debug and reason about it because of the size and the implicitness that often comes with it. So one of the nasty things is that now people can say, oh, I have a dependency on some dependency that is deep in the graph, right? But it's not explicit in your build script. So you look at the build script and say, oh, what dependencies does the project have? But it's not the reality. It has other dependencies, right? Deep in the transitive graph, where they say, new foo, and foo is deep in the graph, and it works, right? So, and for the same reason, it introduces fragility. So you rely on this deeply nested transitive dependency being available, and then someone removes the parent transitive dependency, and boom, your compiler is not working. You wonder what is going on, right? And all these terrible, terrible horror stories that I've seen myself, combine that with dynamic dependencies, and you're in a wonderful world, right? And finally, many, many unnecessary compiles because of the vast surface area, right? Okay. So, hey, Pepper, why not use the direct dependencies and nothing else, right? That would be a good solution. That's what I thought many, many years ago. So the very first version of Gradle from quite a while ago, it was before 0.1, right, was using non-transitive compile class path, right? And, but for reasons we will discuss soon, it had some issues. And I thought, okay, let's switch back to transitive as a temporary kind of solution until we really tackle that issue. It took longer than I thought, but hey, here we go. So the short story is, though, the new normal with Gradle, right, will be that compile tasks are non-transitive by default. For the existing build, it's an opt-in. You need to say, I want to use this new model, right? We don't break existing builds, right? But in any case, that will be the new normal. But what did we do better now than with my kind of naive first attempt quite a few years ago? So yeah, let's look at some demos. So the demo, some of those capabilities are already in Gradle core. Others are still spiked in a plugin, but it's publicly available, so you can reproduce all the demos. But it's not just with Gradle core. You also need to apply this plugin. That will change soon. We're moving very fast in getting this all into master. Okay, so okay, here we go. So here we have that project I described in my graph, right? Root project with 3 subprojects: core, utils, and sumlib. Okay, so if we look into IntelliJ, yeah, okay, so we see this is the core project, and it depends on commons collection, and it depends on the utils project, right? Okay, then we go into the utils project, and it depends on sumlib and on commons lang. Okay, yeah. And if we look in the sumlib project, it just depends on an external dependency, commons IO. Okay, so and here we're using, right, the new mechanism. Compile dependencies are internal, right? They're not leaking. Okay, great. So let's see what is happening. So first, there's another capability we have in that plugin that we treat Java platforms as first-class citizens. So you can now easily say, oh, I want to develop this project for Java 7, Java 8, Java 9. I have no time to talk about that in details today, but also pretty exciting feature. That's why we're saying compile Java 8 here. Okay, so we built utils, and I added some debug statements, right, for the purpose of the demo. And you can see while building utils, right, compiling utils, sorry, we have sumlib in the class path and commons lang, right, but not commons IO, which is a dependency of sumlib that is internal. So it's no longer leaking. Everything worked fine. Why did I switch back, Pepper? I don't know. Must be a reason. Yes, so must be a reason, hopefully. Okay, now let's build core, right? And well, the core build fails, right? So and if we look what is happening, first of all, we see utils is in the class path and commons collection, the direct dependencies, right? Not sumlib, not the other stuff. But now the compiler says, hey, there is in the main method of core, in the main class of core, there is an import, right, that I'm not aware of. It's an interface that I don't know. So let's go to the main method. And here we see we import com-acme sumlib function, right? And here we create an instance of that. And here's the interface. And we see the interface lives in sumlib, right? So it's in one of the transitive dependencies, right? So You could now say, well, that's simple to solve, right? What would be one solution? Just add it, right? Just go to the build script, right, and add compile, depend on sumlibs, right? And but in this case, it's not the right solution. It's wrong, because we don't depend on sumlib, and I will explain you why I think that is the case. So if you go to the main method, the only reason why we create that function object is because the string utils class needs it as an argument. It's part of the public API of string utils, right? They enforce to us that we have to use function, right? We have no other reason to use it. It's not part of our code. It's part of the usage of the utils project. Another example, even more kind of, I think, obvious. Let's say you have a dependency on foo, and foo has a class fooServlet that extends HTTP servlet defined in a servlet API. Now in your class, let's say core, you want to write core servlet extends fooServlet. You need servlet API in your compile class path, right? It's part of the API of foo in this case, right? So, and we want to make that very, we want to allow you to be explicit about that, right? So, yeah, so we could now go, if you look at the Spring Utils method, right? You see, here's the Spring Utils method. Oops, where is it here? And you see it's part of the interface, right? So what you can now, what you will be able to solve that problem, we have a nice little addition, and that is why we can make it work. You can now tell, hey, this dependency is part of the API. So in utils, you can now say sumlib is part of the API, right? So whenever you have a dependency on utils to compile, you will now also get sumlib, right? And yeah, and once you do that, and you compile, everything is fine. But we still don't have commons IO in the class path, right? And we also don't have commons lang in the class path, right? It's just sumlib, right? So, okay. Nice, right? The vicious circle is broken. So, so it's kind of a partially transitive compile, right? But mostly non-transitive. But it's usually the exception. The norm will be just it's non-transitive, and you have dramatically reduced the surface area of your API, right? But it solves one part of a bigger problem, right? Defining your API. The transitive part is one part of your API, but there is more to that. So when core depends on utils and sumlib, it does not depend on all classes of those modules. I hope your code is in a little bit better shape than that. Let's put it like that. Could be, but that, yeah. So there are internal packages in utils and in sumlibs that should not be required to compile, right? So wouldn't it be nice if we can further reduce the surface area of the API, right? So next demo. So here we have the utils project. And there is a string internal class in a com-acme utils internal package, right? And it provides this wonderful method to capitalize strings you pass to it, right? So, man, that is so cool, right? I want to use that, right? So I'm now back in core, and I say new string internal, right? And apply and devox. I want to have a nice uppercase devox string on my output. Okay, it saves me so much time, right? So I love those internal classes. They're so valuable. So, okay, now what does Gradle do, right? Okay, let's not. I did only clean builds to show you the compile debugging statements. We usually don't do clean builds. So everything worked. Damn, right? So. And it makes sense because you have utils jar in the class path, and it contains the string internal method, right? So, so the team of core is super happy, but the utils team is pissed off, right? They're always reaching out to the internal API. So that means at one point they can't refactor anything, right? Once they refactor something, oh no, I'm using this internal method. You can't do that, right? So they're saying, I'm early adopter, right, of the latest Gradle version. And let's do the following. Let's go to the build script and let's stop this craziness. There's now a new API keyword, right, where you can say, hey, I only export this package, and it's not the external package, I guarantee you, right? So you only export this package, and now when core depends on utils, the compile fails, right? It says, I don't know string internal, because it's not exported, right? So you have now the possibility with Gradle, at the moment experimental, you have to use that Spike plugin, but soon it will be in core, right? To enforce your APIs, right? And I think it's so important, right? Big API surface areas are expensive. And the larger the surface area of an API, the more expensive the API is, right? So, and that is true whether you provide an API to other teams in your organization or to the world, it doesn't change the fact, right? They impose massive refactoring constraints, right? They require elaborate testing, right? The bigger your API is, right? You need to have tests to make sure you don't break the contract as you're moving forward. And the less you have to test, the better, right? And the problem gets even worse in multi-repo scenarios where when the API is released independently from the consumers, right? Even in a monorepo, this is super helpful. But in a multi-repo, you have all these different versions. Now that depends on your that use different version of your API. That makes it even harder to do anything, right? So, and that can bring your development speed to a crawl, right? So talk to the JDK folks, right? It took them years to finally modularize, right, the JDK, right? Because they were so, it was really, really hard to evolve the JDK any further. And those are one of the best engineers in the world. Talk to us as a platform provider, provides an API to the world with 2.5 million downloads per month. It is hard to guarantee backwards compatibility, but at the same time continue to innovate, right? So, and the key thing is reduce the surface area of your API, right? So, is that an ecstatic opinion? Well, I don't think so, but in the Java world, I would even say, well, it's at the heart of Java 9 with Jigsaw, right? Define your API and your implementation. So, it is a, and that is another part of our story with that feature. Gradle not just makes it extremely easy to enforce APIs, it also paves your way to Jigsaw, right? In various ways. First of all, we make it super easy to deal with multiple Java platforms. You just say, oh, I want to add target platform Java 9. That's all you need to do, and then you can build for Java 9, for Java 8, whatever you want. You don't, all the wiring is done by Gradle, and when you say, I want to compile for Java 8, you have a dependency, Gradle will figure out, well, you want Java 8, so I get the Java 8 variant of that dependency, right? So, and when you use Gradle, and the good thing is you prepare for Jigsaw in a way, but at the same time you get the immediate benefits from Gradle, at least enforcing at build time the API, right? And you get ready for Jigsaw, right? And finally, what we also do for Jigsaw, we create a module info, we create a multi-release jars. I don't know who of you knows about the details of Jigsaw, but basically we create Jigsaw modules for you out of the box just by adding Java 9. And we translate the export metadata you give us into module info information, so it's pretty cool. Okay, so finally, okay, and then it can look like this, right? Target platform, Java 7, Java 8, Java 9, and you can even specify Java version specific dependencies. You can say, hey, the Java 7 variant of my dependency depends on comments collection 4.0, right? And the Java 8 variant might depend on 4.4, right? So it's pretty nifty. Okay, finally, last thing I want to talk about, compile avoidance, right? What you get out from this feature. So you get compile avoidance now. Whenever a transitive dependency changes, any code changes in an internal class, and any change in the implementation of API classes. So let's look at a quick demo. Oops. Everyone still? No earthquake? OK. So I just built core compile Java 8. So everything was up to date, right? And what I do now is I change the dependency of utils, right? Sorry, not of utils, but I change the dependency of utils, right? Comments lang to a different version. And I rerun the build, and you see utils need to be recompiled, but core is up to date. It's not leaking, right? It doesn't trigger a recompile of core. OK, that's good. So next thing we do is we change basically the public signature of an internal class in utils. We rename string internal to string modifier internal, right? So, and utils is recompiled, but core understands, hey, this is just implementation. I don't depend on that for compile. I don't need to recompile. OK. So finally, what we also can do, we go to string utils. This is part of the public API of utils, right? But I change only the implementation. So I extract a variable, right? So I change the implementation of that method. And we have now mechanisms in Gradle that we figure out, hey, it hasn't changed the public signature of the utils API, so I don't need to recompile core, right? So, and just to make it, but if we add another method, right? So let's add some other method. That will finally trigger a recompile of core. Now the API has changed, the public signature has changed, right? And the way we do that, you might be wondering what this compile Java 8 API jar is about. We basically take this jar and then strip it of any private method of any implementation, right? It's basically a skeleton jar, and we can compare, has this skeleton jar changed, right, compared to last time? And if not, we know we don't need to recompile. So that's basically how we implement that. And yeah, and just for the fun of it, if we add a private method, right, this will not lead to a recompile. So the thing is, yeah. So the thing is, you might be wondering, OK, that looks kind of nifty, but it's anyhow always 1 second, right? So what is the big deal? Why do I think this is worth mentioning? And I even think it's pretty spectacular in the effect it will have on your developer life, right? So let's look at a more real, kind of medium-sized project, 190,000 lines of code distributed over 19 sub-projects. And it's pretty sane dependency graph, right, between the 19 projects, right? So what happens now when we change something in project 1? OK, so the last demo. So when everything is up to date, right, things are fast, right? So now I just change a dependency. This is using the old Gradle model. So I change the dependency in project 1, commons.io from 2.5 to 2.4. And now I run compile Java again, and it's like, OK, come on, please. And 10 seconds, 11 seconds. Yeah, it's not killing you, right? But it's not necessary, right? And if you look in large projects with their crazy dependency graphs, right, and the vast surface area, basically whatever you do, whenever you do an update from Git, it will introduce a massive new recompile because it's so coupled, right? And that is, and many of you know projects and work with projects that have a longer compile time than 10 seconds, right? So And what you want to have is something like this, right? So only project 1 is recompiled, we figure out nothing has changed, and boom, everything else is up to date, right? So, and you will have that very soon with Gradle. So, yeah, those are some. So here we have performance aspect. When we talk about build scalability of that feature, we have enforced software health, right? So there are a couple of, I think also ease of use for developers to make it easy to, hey, this is my API, this is my implementation. I remember, Luke, in 2012, you tried to create something with Ivy to model API implementation. It was a complex beast, right? And it's still in the samples directory. So for historical reasons, it's kind of 2012, yeah. So, okay, and another important aspect of build scalability is having insights into what is happening. You as a build master, how are the developers using the build? What are their problems, right? What are the, and that is a whole new world that we are opening up with Gradle Cloud Services and Gradle Enterprise. So Luke and Etienne will present next. 5-minute break? Okay, good.
Thank you.
Yeah, thanks.